This is Tammy Katz, Chair of the Requirement Working Group. We are hosting our March meeting. We have a special guest speaker today. Dr. Daniel Herber is a professor at Colorado State University, my alma mater. Very happy to have him here today. Louis Kraft and I really appreciated seeing a paper that Dr. Herber wrote with a few others regarding model-based structured requirements in SysML. We asked him to present on this topic and share a little bit. We have a lot of folks who have been asking for information on how do we model requirements. I think this is a great topic. I understand some folks have questioned, is there other ways to do it than SysML? Of course there are. This is a focus for today's talk, but we have other ways that could be presented in future meetings, and anyone who wants to bring up talk on that, we're more than happy to have others share as well. Thank you for joining us today.
Thank you for the invite, and I'm excited to talk about this kind of topic, especially with all of you. We have one paper on this, so we've just started developing this idea. A lot of what you'll see here is based on some things from this group, from some people I already see on the call here. Really trying to leverage the capabilities of SysML to maybe do better requirements. What we term this is model-based structured requirements, and we'll kind of go into why we give it that particular name. So quick outline, very short introduction, kind of motivation here for what we're trying to tackle, and then I'll give a description of the model-based structured requirements, kind of how do we incorporate this using the SysML extension capability with stereotypes. I'll give a set of examples, both kind of defining requirements, but also, now that you have them in this particular format, what can you do with them? Why would we want a more model-centric requirement in SysML, essentially? And then finally, conclusion, future work, some discussion questions to perhaps promote some broader discussion on this kind of idea. All right, so this slide is one that most of you on the call are likely familiar with. The center of the rules governing system are requirements placed on it, often by various stakeholders. These requirements help guide the system development process of a complex entity. However, requirements do not specify how the system will necessarily meet these needs. It is up to the solution and the project team to decide how the requirements shall be fulfilled. One thing here that we're kind of putting forth is a lot of times SysML or other things like that are the techniques and tools that are more and more being used to address that solution angle. So, how can we perhaps make requirements be brought closer, more naturally integrated into those activities as well? Therefore, it's critical to have a well-defined, complete, and adaptable representation of the requirements. And as we know, there are a variety of approaches for developing and managing requirements. Just as an example, there might be these different characteristics necessary, appropriate, unambiguous, complete, singular, feasible, verifiable, correct, and conforming. And we put forth in some of this work that the model-based structured requirements at least is towards addressing some, not all of these characteristics in the way it's structured, essentially. You'll see references at the bottom of the slide, as well as I'll go through a list of them at the end. First slide, pretty basic. Let's get into more nitty-gritty of why we're doing this. It's unfortunately still a common problem of tremendous effort being spent understanding and interacting with requirements, along with multiple iterations, because these guidelines and rules must be adhered to manually by engineers. Or at least, progress is slow in making it so we can help guide engineers do this, in a more automated way, is at least the perspective that we'll have here. These issues can lead to increased costs and risks during development due to poor quality of requirements defined in the early stages, the inability to adapt the requirements when things change, inability to keep them consistent as the definition of the system changes, as the solution itself evolves, and things along those lines. Now, as I already mentioned, architecture-centric practices are gaining widespread acceptance in systems engineering and in engineering in general. This process, these techniques involve capturing the structure, behavior, and rules, and the relationships to create an abstract representation of a system, often termed, a certain type of model of the system. And a common way of doing this, a common standard to represent systems, is the systems modeling language to create a model that achieves some of the goals I listed above. However, this model does not inherently provide value to the SE effort. Rather, its benefits are realized through support to various systems engineering activities. It's the common definition and perspective on a lot of the MBSE approaches, for example, is how does it support various systems engineering activities? So we want to understand here, can we be supporting the requirement side more with the model-centric approach that we're going to put forth here? So the model itself of the requirements is supporting the requirements engineering activities. Now, you may be asking, okay, SysML has requirements in them already, right? Great that, they're there. What are we adding to this, and why is it not, model-centric requirements in the parlance that we'll use here? One identified issue that we have is that many of the existing approaches do not fully integrate requirements with the system model, including what we term classical SysML without the extension that we're going to propose here. So as an example, I'm taking a quote from the Practical Guide to SysML book. SysML includes requirements modeling capability to provide a bridge between the text-based requirements that may be maintained in a requirements management tool and the system model. Continuing, this capability is intended to significantly improve requirements management throughout the life cycle of a system by enabling rigorous traceability between the text-based requirements and the model elements that represent the system design, analysis, implementation, and test cases. A couple of things here, and we're not necessarily disagreeing with any of the statements here. There's a lot of reasons, and this is one of my questions at the end, to leverage requirements management tools, and a lot of the perspectives around how to interact with requirements in a SysML context is through that perspective. And you see the term specifically text-based requirements as well. In fact, the title of the chapter in this book on requirements uses the word text-based requirements. It's still very text-centric. And as we'll see with the rest of this presentation, there's some potential disadvantage of a text-only based description of the requirements. So this perspective we see has less to do with defining the requirements. It's saying perhaps they're already defined in this textual description, and more to do with the traceability to the system model, which refines things and adds additional clarification, formal links that we want to continue to have with the requirement elements and the risks of the system model, essentially. So what we're kind of putting forth here is that the requirements definitions themselves, in addition to the traceability, a part of our goal here is to show how we can use existing SysML concepts and add to it. We're not fundamentally necessarily redefining what already exists. In addition to the traceability, the requirements definition can benefit from direct relationships to the system model and SysML constructs more broadly. So to this end, we are describing an approach for supporting rigorous model-based requirements using existing concepts of structured requirements in SysML, termed model-based structured requirements, or MBSRs. Okay, so quick introduction. Now let's talk about model-based structured requirements. You may be familiar with SysML or structured requirements, but not both. So I'm going to give an overview of the fundamental concepts, and then we'll merge them together in a SysML model. Structure requirements or requirements template defines an orderly requirement structure with specified attribute placeholders. Some of the intention here is it helps capture the precise meaning and communicate the required information to complete a requirement. One example here, the who, shall, what, how well, under condition. We see things in brackets that are bold. Those are different attributes that are intended to properly define to define a complete requirement. Here are the definitions of those different pieces. The who defines the subject term specified by an agent or user role that provides a capability or performs some function. The what refers to an action verb specified by required functionality or characteristic. Continuing how well indicates some comparison factor specified perhaps by constraints that can be applied to restrict the implementation of a required functionality or design characteristic. Then finally, we have condition. All this needs to be under some condition that describes a measurable, qualitative or quantitative terms specified by characteristics such as operational scenarios, environmental condition, or a cause that can be stipulated. Essentially, this is giving a lot more structure than saying, write something that helps me ensure the system does what it needs to do. Rather, this is giving a much more specific, much more standardized way of writing the requirements. For example, actuation system, which is the who attribute here, shall prevent inadvertent stowing, which is the what, with at least 3 levels of safety, the how well, under normal deployment operation, the condition. As currently presented, the thesis we put forth here is that this is really a refinement to the classical textual requirements approach, as it is only an imprecise relationship to the system model. So for example, the actuation system or the actuation system who, well, in the system model that we may create for the variety of systems engineering activities we might be completing, there can be an actual element that is a representation of the actuation system. So rather than simply having the actuation system as a well-defined placeholder in the requirement, what if it was a direct link? What if the actual who attribute is defined not through a textual statement, but through the model element that represents actuation system. So that's where we'll be going with this kind of idea is using these templates and using the elements to fill those templates in through kind of the SysML modeling side of things. There's more that can be done here. This is not one particular template, as you'll hopefully see from when we go through how to describe this specific type of structured requirement in the model-based context. It can be applied to other standards and approaches as well. Very common one, I'm sure many of you are all familiar with, the condition, subject action, object, constraint of action version of this. But we would put forth that it's the same idea, right? There are these placeholders that can be modeled with the SysML modeling language and use elements to reflect what the object is, what the condition is, what the subject is, etc. An example for this one, similar idea at C state 1, wouldn't it be great if someone who wanted to understand what C state 1 is in the condition had more information, right? In the context of a system model built in SysML, that C state 1 might be more fully defined through a variety of things. It might be a block with a bunch of attributes that define the wave conditions and other factors. So even though it's in the requirement statement as C state 1, there's an element that provides, to whatever degree is necessary, information clarifying what that condition is. And the same thing can be true for radar system shall detect targets at ranges of 1 to 100 nautical miles. Wouldn't it be great to know, we have this targets object, and maybe over time, the targets that this radar system needs to detect for changes. Well, we would have a formal linkage between the targets object in the model and things that are placed within that targets category. Final point here, there's a lot of other structured requirements forms. We've really only pursued this one that was on the previous slide, but I foresee a lot of potential work that can be done making kind of some sort of standardization. So the application for functional, non-functional interface design, operational, other requirements, forms, attributes. We'll get into not just the structure that we see, say, in equation 2, but also what types of elements might be put into these different categories. Because SysML is very broad, we can also use those constructs to limit, to say the condition can only be a constraint block, for example, or the subject should be some sort of structural element or a block. Action should be a behavioral element. That type of additional tailoring might be done. A little bit of background on the classical SysML requirements, as again, our intention here is to add to it rather than remove from it or modify anything specifically. So as with many aspects of system modeling, SysML supports the inclusion of requirements. The classical SysML-based requirement is developed by defining a few things. There's these 3 abstract predefined attributes, name, ID, and text. From there, there's traceability relationships, including owner, derived from, satisfied by, refined by, traced to, and verified by. And then finally, there's kind of hierarchical relationships between requirements. So we can say, a requirement contains multiple other requirements. But this is a reasonable overview of kind of what is possible using the kind of standard-based definition of requirements in SysML. And we see the focus on at least initially defining what the requirement would be is through the textual statements in the abstract attribute at the first bullet here. Even though some relationships between the requirement and the system model are now possible, especially through, we'll say, the traceability relationships are often used to represent how the requirements are related to the system model in whatever form, whether it's what's verifying it with test cases or what's satisfying it through a block or something along those lines. Again, the definition of the requirement is often still relatively static, which could be more complete, could contain errors. It could be inconsistent with the rest of the system, with the rest of the SysML system model. Again, my example is if you are still early stages of defining the system, what the system should be subject to, the names of things may change, and keeping those consistent might take effort. In this approach, those would be automatically managed by the SysML tool, essentially. Here's an example. This is meant to be comparison to proposed approach. This is just a representative SysML-based requirements diagram showing initial time to deploy type of requirements with its ID and text statement. And we can have a bunch of relationships to other things, derived requirement relationships, containment relationships between higher level requirements. We can provide some more specificity. This less than 2 seconds might be formally defined as a initial time to deploy constraints, getting perhaps more towards like an executable requirement that allows you to verify if it's true or false, to satisfy and verify by as well between the system block and the test case. But Again, the main thing here is that the definition of the requirement is still relatively static at this point in time, rather than being based on the model elements themselves. It has some relationships through these satisfy, verify by, refine by, but it doesn't have the definition itself perhaps fully integrated into the system model. To address some of these concerns in terms of the gaps that we see in kind of the SysML modeling constructs for requirements, as well as the benefits we see from the structured requirements perspective, our goal here is to kind of combine the two together to leverage the advantages of both. So we want a more rigorous approach for structural requirements that is directly links to the SysML system model elements, similar to the existing traceability relationships, right? We like those traceability relationships. That allows us to detect changes. It allows us to keep things consistent. It allows us to reuse content, that type of idea. With direct links to the system model, this approach to requirements is more heavily model-based and structured. Again, if we are perhaps defining some, if not all, of the requirement itself through the model, then we're saying it's more model-based versus textual-based, and structured because the mechanism we're going to use to make that happen is through the structured requirement or requirements template perspective. That's why we came to the conclusion to call this approach model-based structured requirements. Let's get into kind of how we are formally doing this in kind of the SysML context. We are using the SysML as extensible through things like the stereotype mechanism. To do this, we are going to define stereotypes, and I will zoom in on that figure on the left in just a second. We will be defining a structured requirement stereotype. In particular, this work focused on the template from equation 1 that we had before. So we had the who, what, how, well condition side of things. Again, we are basing this off of the existing SysML stereotype. So we can kind of see the heritage going down from the SysML profile to the requirement stereotype class that's used, that the stereotyping classes for defining the SysML, classical SysML requirement type. So our goal here using the generalization relationship is to inherit everything from that. So we're building upon that classical requirement definition, and we're going to be adding different attributes to the definition of a requirement that we will now call a structured requirement. So we'll focus on the main ones that we were talking about before: the who, the what, the how, well, and the condition. Those are now attributes that would be applicable to a structured requirement that you would fill in using the typing notation here, the colon notation. We are specifying what types of model elements can be put into the particular attribute. So in this case, the who is being constrained to be blocks in the model. And then finally, we have multiplicity as well. I have these in some bullet points that we say there's one thing here. So the requirement is applicable to one thing and one thing only. And at this point in time, structured the definition of the structure requirement. One block is applied to the who field. What is more broad? It can be any type of behavioral element. How well is a constraint block. There's no specificity on how many there might be to fully define the how well part of things. Condition is any named element. One through many can be applied there. Just again, I want to emphasize, especially if there's more specific guidance you want to provide to someone creating the requirements, you can use the type instance approaches in SysML to better constrain what is allowed to be placed in the different attribute fields. So again, that's the definition of structured requirements. Adding those attributes are relatively straightforward with this particular mechanism. Each attribute is typed by a SysML model element, several powerful consequences. I've gone through a few of these. One, we can enforce that only particular types of model content is valid for a particular attribute. Again, I said the who attribute must be a block as one example here. It also allows us to pick from an auto-generated list of available elements in most SysML tools. This promotes consistency and understanding, does the system model contain the thing that I'm trying to represent in the requirement itself? If not, then that indicates I need to create it. So in the tool, if I am trying to add something to this who attribute field, I can get a list of all available blocks that are currently in the model and select the appropriate one to apply to this attribute. And then finally, the multiplicity notion. Again, how many are there? You can give that, again, more structured guidance. Part of our vision here is that you can be even more structured by using some of these SysML modeling concepts with the definition of the structured requirement. An MBSR element can be created by applying the stereotype to an existing requirement. So this does work if you just simply apply or refactor an existing requirement, and it will allow you to have those additional fields show up, or simply create a new requirement that is based on this structure requirement definition. And then you specify the attributes necessitated by the stereotype. So a basic example is shown here. This example structure requirement, we're just showing this is one example of it being applied. So again, we still have the elements of the abstract SysML, classical SysML definition with a textual statement here that we've manually at this point filled in with the structured pattern. But what we see with the addition of the structured requirement attributes is we now see the condition is defined by a model element. This model element is an activity called normal scenario. So that, and the icon is indicating that it's a SysML model element. This activity might include a whole set of diagrams and other things, other content, other information that really helps the engineer understand, or it's the location for an engineer to place that additional information for someone to define what does normal scenario look like, or understand again what it is. How well is a constraint that we're calling limit in this notional example. What is implemented behavior? Again, it might be another activity. And then who is some component, some block, again, that might have a lot of information associated with what that is in and of itself. Part of our goal here also was, if we seek to define requirements in the SysML context, there are other things that might be needed before someone would be willing to do this requirements definition fully in a SysML tool versus in more robust and tested requirements tools. So we wanted to also demonstrate that using SysML contracts integrate organizational attributes into the fundamental definition of the requirements that will align with the specific rules and policies of the organization. The reason to add this here is to say that, in addition to the structured requirements, we can add other attributes and have perhaps a more holistic, policy compliant, high quality definition of a requirement with this. In this case, we define an additional group of attributes that is, more organizational specific, perhaps the organization requirement attributes, things that we added again in this particular paper: compliance status, version number, priority, qualitative assessment, implementer, tester, verification means, etc. Maybe I won't zoom in here, but you can see, similar to the structure requirement stereotype, we have an organization requirement attributes stereotype defined with these properties. These properties can be defined in a certain way, an enumerated list for the compliance status, the list on what they are. This is not necessarily new, but this is, again, demonstrating that we can add in all the content that we might need to have a really well-formed requirement in our opinion. And then finally, we merge these two together in what we call an organizational requirement that combines the organizational requirement attributes and the structure requirements definition into a single, more well-formed requirement type. You could just use the structure requirement type, or again, add these additional properties that have a more complete requirement definition. Here's an example kind of comparing it to, think of our previous classical SysML-based example here, where we have added in some of the organizational requirement attributes, and I won't focus on those too much, but those are there. We've added in the structure requirement attributes, who is TRAS? This, I guess I haven't get the acronym, it's thrust reverser actuation system. It was the system that we were using to explore this concept. What operate TRAS? There's a lot of details not specific to the name of that element, but the details of what operate TRAS means is defined in the activity model element. How well and condition. In this case, we actually had two different conditions here to show it's both in the normal scenario and there needs to be condition for the actuator deployment. So it's a combination of conditions that need to be true for this requirement to be properly defined. We still see the traditional SysML traceability and hierarchical relationships applied because we still see that those are quite valuable to a well-defined requirement in a SysML context. So a couple of additional points on the potential benefits we see with this approach. So connecting requirement attributes with model elements allows requirement information. Now we see both perhaps the definition and the traceability to remain current and available. I define in this initial time to deploy requirement the who attribute, but TRAS, that's their top level system block, right? That may evolve over time, and it might be good to have a formal relationship to the thing that defines our current understanding of the system of interest, or the whatever the who attribute is for the requirement in the definition of the requirement itself here. So we see this potentially reducing errors and iterations when developing requirements, saving time and other resources. You might define things once and then allow that relationship to embed changes in a more automated way. We also potentially see it simplifying activities such as dynamic change impact assessment. For example, if this block changed, what requirements definitions depended on it? So someone updates a block, you can run analysis because now there's a formal link that says, well, do I need to revisit these requirements because a particular attribute was defined with something that changed? So, this is also the same idea with the other traceability relationships that already exist. You're adding those relationships perhaps can allow you to better keep track of what you need to pay attention to as things change, as things evolve throughout system development. By formally breaking down the requirement statement into required attributes as model elements, completeness metrics can be automatically computed, and its gradual definition might be less risky as well. I'll talk about more completeness metrics, but also gradual definition might be less risky kind of means, there might be, aspects that are missed and you can readily add them in or have placeholders established. You see kind of by having the formal attribute placeholders there, the requirement might not be fully complete, but you know that it's missing something, for example, and that needs to be added to fully complete the requirement. And then our final point here is there might be a deeper, more natural connection between the requirements team and the other engineering groups through the single source of truth SysML model. So I'm sure you've heard, if you aware of the SysML kind of idea and its connection to like the MBSE type of paradigms, there's this idea that there's a single source of truth that defines the system development and the system itself. One perspective might be if you're able to do the requirements development you need to do in the same location that the other engineering teams are doing their activities, then there's not a need perhaps for another tool. Not saying that that's going to work in all cases, but that's just kind of an idea that might be interesting to think about in terms of the more natural connection between the various things that we're defining in the quote unquote single system model versus multiple models that define our development activities. Okay, so I given a couple really high level examples, but now I want to get into some more specific examples and especially give some kind of comparisons between some traditional approaches versus our proposed approach here. So we'll look at some examples of MBSRs and have pure textual structured requirements as well as classical SysML structure requirements for comparison over a few different slides. All these examples are based on a notional thrust reverser actuation system, a necessary subsystem in most commercial aircraft to achieve and maintain safe ground stopping distance after touchdown in adverse conditions in particular, such as wet, slippery runways by reversing fan bypass airflow. One thing I'll point out now, and I'll point out a few more times, the model and these examples and the stereotype definition, the diagram you saw before, we made it publicly available on GitHub for anyone who wants to potentially look at it. And you can import perhaps this definition of the structured requirement stereotype and play around with it and try it out on your own. So please take a look there. It is for, in particular, Cameo Systems model is the tool that we use to implement the SysML model at this point in time. We have here a definition of textual requirements. We see it perhaps as in this tabular form. It has ID, name, requirement type, text, rationale, right? There could be more columns, but the idea here is that it is relatively static representation of what the system needs to do. It's defined again in that kind of informal, perhaps human in the loop way in how it connects between the definition of the requirements and the system model itself. So the point here is that much of the necessary information is captured in this pure spreadsheet form. It's not like this doesn't have information that we need. It has the information we need. However, the potential issue that we're thinking about here is the information generally static, unlinked from any other representation of the system of interest. So that's, again, kind of the goal is not that this doesn't contain the information, but rather we want to connect that more to the system model. So classical SysML requirements for TRAS. So bringing the requirements into the SysML context will allow us to do a lot of other things that we want to do. For example, we still have name, text, ID, those basic things that we saw on the previous slide, but now we also have relationships. We're starting to build those connections to the system model with derived from, satisfied by, refined by, verified by relationships to various model elements. So we now have a lot more information connected to the system model through these different traceability relationships in particular. However, we're still left to understand much of the specific requirement and the intent of the requirement, and if the requirement is potentially satisfied in many cases based on its static text-based statements. Maybe I'll point out here, the refined by often is intended to give that additional context that is not perhaps fully captured by the textual statement, but often we see here that these are all refined by constraint blocks, for example. The refined by, you might have to do many refined bys, or there's not, I guess, a very systematic way, I think, to do the refined by to handle the variety of scenarios we may encounter if we want to fully ensure that the requirements, intention, and how it should be evaluated, for example, is captured with the system model. This is the model-based structure requirements for TRAS, again, represented as a requirements table. That is a view generated from the system model that's created based on the model elements we have. So if we kind of zoom in here, we'll see, again, we're kind of adding things to this definition of a given requirements, name, performance. We still currently have a textual statement, but the idea would be perhaps someone, if they understand what the structure of the structured requirement template being applied is, then perhaps all they need is the who, what, how well, and condition columns and the elements within them. The trash, it should operate trash with some initial time to deploy constraint under certain conditions, this normal landing scenario and actuator deployment. So that was the example we saw before. And again, some questions I have is the language here isn't quite specific, but the model's elements that they represent are quite specific. And that's potentially an issue right now with how we're proposing some of these things. This has more detail than just looking at these elements. So should be, for example, naming elements so that they have the information needed to construct a full textual statement from it, for example. In any case, the elements in a well-defined system model will contain all the information needed to understand this how well initial time to deploy attribute, the how, the what TRAS, how to operate TRAS, and the who in terms of, that's what it is. It's on the TRAS system. It's a block in the system model. And this includes the other things as well that we might have. But for the interest of time, I'll just focus on these 4 columns that are specifically linking model elements to the structured template that in concept defines the requirement. So we now have more specific information about each requirement, and this information comes in the forms of links to the model elements. For example, do you want to know what normal landing scenario is? Go to the element that defines it, right? That's kind of the interaction paradigm that we put forth here, is that an engineer would go in and see what the definition of the normal landing scenario is if they need that information. And then following up with that, if the normal landing scenario definition changes, and many tools allow you to check your version 1 versus version 2, what changed? Well, if normal landing scenario changed, it might be good for someone who has ownership over this requirement to make sure that it's still appropriate for the change in the normal landing scenario definition, for example. So it's a more granular change assessment that might be done because we've granularized the requirement through the structured attributes. I really like this representation because it kind of really shows once we've captured things in the model, there's a lot of things we can do that might be more challenging to do with other approaches. So on the left here, I have a model-driven dependency matrix. On the top, we have the 7 sub-requirements and 1 main requirement shown. So these represent those elements. And then on the bottom, we have model elements. We have a bunch of things in our behavior package that are a bunch of activities. We have a bunch of constraints in our constraint package. We have a bunch of things in our structure package. And when we consider the different attributes now, there are formal links between the requirements and the different model elements. And some model elements might have multiple links to multiple requirements. The legends here, the blue is saying that there's a relationship. It's the condition type of attribute. So if we go to this initial time M.1, that the normal landing scenario is in the condition attribute field for this requirement. So we can kind of see some higher level analysis that normal landing scenario is related to 5 different elements in the condition field. We can do this for a bunch of different things: TRAS, power interface, hydraulic interface actuators, understanding how many requirements are related in a particular context here, right? In a particular attribute context, for example. So we can get these high-level summaries of more specifically how the system is integrated into the definition of the requirements, and just a better link between the requirements and the system model. You can tailor these views for your particular needs to understand your system, especially as the number of requirements grows. You might want views like this that help, synthesize down into numbers of relationships between a certain element and other requirements. Or again, if someone's responsible for landing scenario and the definition of it, they know which requirements are using it in its condition attribute definition. So more so than the classical SysML approach, we have shared model elements across the MBSRs, automatically visualized with this dependency matrix that we just discussed. TRAS is shared among multiple elements, as well as operate TRAS and normal landing scenario. Again, we can kind of see what are the elements that have the most relationships to the requirements. Maybe those are the ones that are most critical to discuss and understand and make sure to define correctly because of their strong linkage to many requirements. And this also can be used to build up the requirements. You can imagine that all these arrows are not there. And the idea would be, well, how do I really define initial time to deploy? Well, I really need to add the normal landing scenario to the condition. So I could add from these views those elements. So I'm using the model elements to define the requirements in that direction versus this is more of an analysis direction. Metrics as well, something that's been well established in the literature, that understanding quality metrics and completeness metrics, things like that on requirements is of interest. And using this approach allows us to do some formal metrics analysis on the requirements from perhaps a completeness perspective in particular. So again, early work here. So we put forth that a requirement is complete if it has each attribute defined. So we see here, we say includes who, includes condition, includes how well, includes what. So we can see how many requirements have these different fields, total number of requirements, and then the completeness percentage. Well, only 38% of our requirements are complete because some of them do not have some of the attribute fields fully defined yet. Versus in the next iteration, we can see that many more have those fields filled in, so the requirements are more complete. And again, our definition of a complete requirement is that all 4 attributes have one valid model element applied to it. This might be a way to automatically assess a requirement completeness with respect to the MBSR specification. For example, we're considering non-empty attributes. The metrics can be automatically computed in the model using customized metric execution suites and scripts. And this is a space where I really see there's a lot of potential to define a better requirements completeness or quality metric. And for example, you're assessing rather than just is it empty or non-empty, there's some other scales that could be applied, some more aggregate formulas to pick apart the requirement based on the attributes. Maybe something's there, but it's not defined as complete yet, then you don't call the requirement complete. That's not quite implemented in the metric suite that we defined in the model that I shared. If you saw from the previous slide, the top level requirement didn't have the attributes because it was really just the capture point for the other 7 sub-requirements. So that one technically in this definition is not complete. So in other words, more thought needs to be done here, but I want to put forth the idea that having the structured attributes in the model context might enable some very interesting ways to look at a variety of metrics, whether it's quality or completeness or what. And I won't go through the code here, but I wanted to highlight that a lot of these tools, once you have that information available, you can define a script like this that goes through all structured attributes, all who attributes, checks if it's empty, and does the metrics on them. So leveraging the model-based nature of the definition of the requirements, again, can enable some very interesting automatic interaction mechanisms and capabilities that might not have been readily enabled before. So this is a Groovy script in Cameo system model used to count the non-empty who attribute. It illustrates the possibility for a deeper programmatic interaction with the requirements is how I'll put it. And full details are again available there at the link below. Conclusion, wrap up pretty quickly. When requirements are written in a classical text format, significant resources, including many brains, are required to develop and manage them, which can lead to identifying problems sometimes later in the development cycle. So overall, the proposed MBSR approach is more aligned with the model-centric philosophy of system development through its more broad use of elements in the system model and its actual definition of the requirements through SysML model element constructs. We also see it kind of add some more system thinking rigor when developing the model. You're thinking of those elements are related to the system itself in its capture in the SysML model. So you now are able to perhaps do more higher order reasoning between, is that element well defined in context of the rest of the system model? Is it completely defined? I think it can add a little bit more rigor because you're no longer just thinking of it as your mental model, but there's actually a formal model available for the element that you are putting in that attribute placeholder. It also restricts us, which we'll put forth as a good thing here, to create and define the right elements and relationships, or readily see that they're missing, or readily identify that they're incorrectly defined. I think it helps in that aspect of things. It also directly connects pieces that help define the requirement to the functional and physical architecture elements. Again, if the SysML adoption for the other system design activities for design, validation, tests, those type of things are being ever increasing. A direct relationship to those is potentially an advantage of a more model-centric approach to doing some of the requirements activities. Future work, validation rules is one aspect. We leverage a lot of the built-in validation rules. The idea of like the who must be only a block in some sense is a validation rule. It's ensuring directly that we cannot incorrectly add a wrong element type to a particular attribute field. But I can imagine more different types of validation rules or different types of things that check the quality of how the element is named or things like that. Things that already exist in literature might be a way to really take this to a more effective level. APIs and scripting is available in a lot of these tools, automatically generate the requirement text statement using unstructured attributes, something that's already been put forth in general, but you can foresee now that this approach can also support that idea where, do we need the text statement? Or do we need the model elements that can be used to define the text statement? That kind of direction is at least interesting concept in my opinion. More refinements to the attributes, naming, typing, completeness. Again, we have one conference paper on this topic. There's a lot of work I think needed to define what's the right way to structure them. What's the right types? It's not just this is the attribute name, but if you kind of think of the SysML modeling constructs, how should I constrain it based on those modeling constructs so that an engineer is always putting the right type of element into the different attribute fields, that type of idea. Further investigations are requirement and model metrics that we talked about before. Again, very naive, in my opinion, definition that we define for completeness in terms of just need those things filled in. I'm sure many of you have ideas on more effective metrics, and defining a metric suite in Cameo so that it can be executed on your requirements model is future work. Different profiles for different types of structure requirements. Again, there's a lot of put forth a couple and had references at the bottom for other approaches, but this is by no means at the point where probably adopted on a broad scale. It needs a lot more standardization and definition to meet all the diversity of perhaps requirements needs. And this is definitely a space where more examples to push this forward would be interesting. So we're working on that, but I encourage anyone who's interested in this concept to feel free to put forth additional examples that they may have and how to define through a system model the requirements with this MBSR mechanism. So maybe in the interest of time, I won't go through these questions. I want to leave a little bit of time for discussion, but I have some general parting questions here for you to be thinking about. Again, if you want to contribute to this, there's the model available. You can always contact me through that or through my email. You can propose refinements, add additional examples to that. That's available. Please, I'm interested in collaborating on this topic as well, if any of you have interest in that. So with that, I want to acknowledge my other collaborators on the RIS, Jayesh and Cameron at CSU, at Colorado State, essential at especially Jayesh, the student, getting the models working and constructing things here. And this was supported by the Woodward CSU Master Research and Development Agreement. So with that, I will quickly go through the references. I'm happy to make these slides available as well. So don't feel like you need to write anything down. I'm happy to provide these out. And thank you again for the invite. If there's time for discussion, I'm happy to have that now.
Hey, Dan, this is Louis Kraft. Do you have access to the chat window?
Yes.
So we've got maybe 10 minutes. So if you want to scroll through some of the questions in the chat, we don't have time for all of them, but the ones that you can give a response to, if you could address some of those, that would be great.
So I'm looking through, as I said, the model is available. So that was the first one. Where can we insert context to refine the behavioral nature of a given requirement to guide precision? How can you extend the language for scenarios and granularity? Yeah, I'm not sure if I have a good response at the moment. I leave it up to someone who wants to implement this approach in terms of how they want to define the specific nature of any one of those given attributes. So I think you might want to consider how those attributes should be defined so that you have the ability to give the required context. And does the structured requirement provide an attribute that gives you that context is maybe one way to approach this, is that you kind of have an attribute that is specifically included to give you the context that is needed to fully define, as you say, the behavioral nature or whatnot. So yeah, Jeffrey, I don't know if I fully answered that question, but I kind of leave it up to the structure of the structured requirement and the definition of those different attributes to facilitate the additional refinements as it may come across. So I have to scroll down because I did see. So you could still use the refine mechanism, as I said, but one thought here perhaps is that, so say you define a behavior that's a part of one of the main attributes, you could be refining that behavior more specifically than trying to refine the requirement into a use case. And I guess that's a slightly different mechanism that might be useful, because then you're no longer relying on changing the requirements relation, but rather you're changing something that is defining the requirement itself. So I think that could be a way to refine things over time, is that the element itself, that's what you refine over time, right? The details of it, the breakdown of what the behavior specifically means. Lots of questions here. Let's see. Do we need to define upper and lower bounds for behaviors and measure performance in general? So again, that's, I think, an open to the structure you have. So I think we had the how well, for example. That's often the case is, how do you define how well? Well, it might be upper or lower bounds on the measures of performance and capture it in that way. And again, we formally restricted it to a constraint type of element, but I think how well could be done in other ways as well. Yeah, again, the flexibility here is you define what you want those attributes to be structured as, and what SysML element constructs you want to use to capture the intent of, for example, how well, and that could easily be upper and lower bounds.
Dr. Herbert, this is Ron Carson. So I have a question about the euphemistically called non-functional requirements. That was a question that I got posed by the requirements working group about 3 or 4 years ago. So I put together some ideas, but how would you handle characteristics that don't have a behavior? Is it just with a constraint block? Is that the idea? You eliminate the behavior because it's not a behavior. It's just a constraint block.
In the example that we have here now with this mean time between failure that we labeled a non-functional requirement, we mostly kind of said that, how well is with a constraint block that is assessing essentially the mean time between failure value needs to be below some limit. When that is occurring, we did still have a behavior associated with in this case. It's under the operate trash what behavior paradigm. But I guess I would say, you might have a structured non-functional requirement template that doesn't have that behavior aspect to it. And the one that I put forth that you're aware of maybe isn't appropriate for all requirements is maybe one thought here. And the non-functional requirements might need more tailored template to appropriately define what they are. But yeah, I think a constraint block in many cases capture the non-functional requirement needs in the SysML context, at least.
Okay, thanks.
I think our goal in this initial paper was to put forth an initial go at this. So yeah, the who might always be a block, I think is a great point. We have some initial work on combining different, more specific types into kind of a super type. So there might be a who attribute that can be defined as a block or a use case, or you can combine different classifiers in the SysML context to say what the who might be. So this is what I mean by any feedback on refining, especially that initial stereotype definition. Again, it was one initial goal that was meeting our needs, but I certainly don't think it's broad enough and thought through enough to capture all the different scenarios that you may have for capturing a requirement with SysML elements in those different attribute fields. So I'll continue down. There's a question on the model. So again, I think that what we're putting forth here a lot is that this approach would be specifically bringing the requirements in the SysML modeling context. And a lot of the tools have been trying to have the SysML model interact with other types of models, more of, say, analysis type models, things like that. So I think that's a question that was maybe a little bit a part of my parting question slide that I had is, should we be bringing all our requirements into a SysML model? And if that SysML model is going to be serving as a single source of truth versus other different modeling contexts that might be appropriate. But I do think there's a lot of work in having kind of SysML representations of our system interact with other more specific analysis models, for example, with other tools and things like that. So once they're in the SysML modeling context, you might be able to say, run a simulation, run some analysis, get the actual parametric result that you would want to verify, the time to deploy or the power consumption metric, those type of things.
There was a question about if people have different levels of knowledge about model-based work and model-based thinking. I could take that one if you like.
Go ahead, Cameron.
Yeah. This is by no means a standard answer or a final word on the topic. What I noticed is that as long as you have one person or two person who understands the SysML, then people can gather around in the room from different disciplines and different departments. And because the artifacts are so visual, as long as you have someone who can explain to them what the different linkages are and stuff, then they very quickly start contributing and improving the artifacts. That was my experience. And that was the level that was a lot more than gathering around standard requirements, the way we normally do them. Purely because it's much more visual, and much more interlinked, and much more architectural. That was my experience, that collaboration, even with people who weren't SysML experts, among the team was better. As long as you had one or two people who knew it, the collaboration went much better levels, much more than the standard text-based, because our text-based requirements are so complex and large, it only ends up with one or two people. This had the opportunity for much more of the team who are not officially responsible for requirements to collaborate. So that was the small observation I have just in one example of thrust reversers.
Hello, everybody. I hate to interrupt. This has been an amazing topic, but we are at time. And first of all, Cameron, thank you. It's so good to see you again. You and Jayesh and Dr. Herber, I really enjoyed the time working with you all at CSU, and I'm so thankful that you were able to bring this topic to us today. There are a ton of questions here. And so if you don't mind going to that last slide again with your contact information. And I do believe I heard a request to try the model, provide some feedback.
Yes.
We would love for folks to do that, and we can definitely start seeing how everybody has ideas on how to expand on this material. We have other speakers who are interested in bringing other approaches to requirements modeling throughout this year. We are always happy to have volunteers to share their work, so I appreciate hearing and seeing this work. You have his contact information. Feel free to reach out with additional questions. We're going to wrap this one up. Our next meeting is on April 19th, where we have Heinrich Matfolk going to speak about how to assure quality in a set of requirements, particularly when you want to have comprehensibility, but also singularity. So there's some challenges there. And so he's putting together a great presentation to ensure we have just enough requirements, but it's all clear in the requirement set. And I think that's going to be a real interesting talk. So I hope you all join us. I'll send out an email announcement to the team to let everybody know exactly when that is and the Zoom registration links. Thank you all. Thank you to the speaker. And this concludes this meeting.